Hi, welcome to this lesson on calculus, the second derivative. What is the second derivative? Okay, so far we've defined what the first derivative is of a function f. Essentially, the first derivative of a function at a point or an interval tells us how the function changes with respect to the independent variable. So we found things like stationary points, where we saw that it was sort of like turning points where the graph would turn and would have a zero gradient of the tangent line there. And then intervals where the graph would increase or decrease based on the first derivative. So for increasing, the first derivative was greater than 0, and for decreasing, it was the first derivative less than 0. Okay, so the second derivative of a function now can tell us two further things about a function to help better draw an accurate sketch of the function. So what does it do? It tells us the intervals of what we call this word concavity. Okay, so concavity comes in two types of flavors. It comes in concave up and concave down. Okay, so the shapes are as follows. For concave down, what it means to be concave down is that all the tangent lines are lying above the graph. So the graph is below. You can sort of think of the graph as being down. It's facing downwards, and all the tangent lines are above it. Okay, so that's concave down. The mathematical definition for it is that the second derivative is less than 0. And whenever that interval is satisfied, we say the graph in that interval is concave down. Okay, so it lies below its tangent lines. And then similarly for concave up, the graph f of x will lie above its tangent lines up. So that's a sort of notation you can sort of remember it as. Concave down is that the graph lies below its tangent line, so it's going downwards. And then concave up is lying above its tangent line, so sort of etching outwards. So concavity essentially tells us how bendy the function is and in what direction. So mathematically for concave up on an interval, that'll be when f double prime, or the second derivative of f with respect to x, is greater than 0. And then the second thing it can tell us is what we call the point of inflection. So the point of inflection is where the function changes from either concave up to concave down or concave down to concave up. Okay, so we can see an illustration here. The graph here starts off going concave down and then suddenly shifts and becomes concave up. So at that point that it suddenly changes concavity, that is what we call the point of inflection. Okay, so those are the two key properties that the second derivative can tell us about the function and gives us a more accurate description of what the function will look like. So as we said, the second derivative of a function f is essentially the derivative of the first derivative. So the first derivative, that tells us things about the stationary points and where your graph increases or decreases. And then the second derivative tells us how fast that rate of change is actually changing as well with respect to the independent variable. So a nice classical way of thinking about the second derivative is in terms of the concept of speed and acceleration of a vehicle. So mathematically, speed is defined as the rate of change of the distance, we'll call x, with respect to time, which we'll call t. So mathematically, if we let v equal speed, sometimes referred to as velocity, we then have that velocity or speed is the derivative of the distance traveled with respect to time. Now, as you are traveling, let's say you're going down the freeway, suddenly for the first 10 minutes you're driving at 80 kilometers per hour, then for the next 20 minutes you're driving at 120 kilometers per hour. So you're changing your speed with respect to time. So that rate of change of speed with respect to time is what we call acceleration of your vehicle. So acceleration is defined as the derivative of your speed with respect to time, but we know that v, the speed, is already a derivative. It's the derivative of distance with respect to time. So you're applying another differential operator on a current derivative. So you're taking a derivative of a derivative, which is the second derivative. So how fast you change twice in terms of your distance with respect to time is the acceleration. Okay, and essentially acceleration is the second derivative of distance with respect to time. So that's a nice application way of thinking about the second derivative. All right, so let's go ahead and define more what it means to be concave up, concave down, and an inflection point, and then we'll have a look at some questions. Awesome. I'll see you in the next one.